Hey everyone, in this video we're going to be talking about gears in general and specifically looking at force analysis examples. We're going to be doing two examples in this video, and as always this video is part of a lecture series on mechanical design too. So to get started with this, we have a problem written here already for us, so you can copy this problem down or kind of work through the problem as we go through the video. So one suggestion is to try and work the problem by yourself, but this is a first example problem in this lecture series, so we're going to go through it and kind of solve it together. So we're told that a pinion runs at 1750 RPM counterclockwise. So we're going to show the pinion here. So we're going to show that there is a pinion right here. Okay, so I'll erase that arrow, but we have a pinion right there called number 2. That's the first number in our system for the pinion gear. And we're told there's a power of 2.5 kilowatts and the pinion is running counterclockwise. So we already have the movement going counterclockwise. So we can see that if we highlight the movement, it's going counterclockwise. And then that means that the gear attached to it is going clockwise. And then that means that gear attached to gear 4 is going counterclockwise again. We're also told that we have 20-degree full depth teeth, and we have a module of 2.5 millimeters. So since we have a module in our problem, we're probably going to be using SI units as part of our analysis. Now, the question here is, and the question that we're told in this diagram is to essentially find the forces on gear 3. So we're just asked to find all the forces on gear 3. And one of the best ways to do this is to start by drawing a free body diagram and then figuring out all the forces based on the free body diagram. So based on the information that we're given, we actually have enough information to solve this problem completely. So let's go ahead and try and figure it out. So first things first is sometimes in these problems, you're going to have to start with a free body diagram of gear 2 or the pinion. In this case, we're going to come up with a free body diagram of gear 3 directly. And if we need anything from gear 2, we'll try and solve it as we go along. So what we're going to do is we're going to draw a free body diagram of gear 3. And I've imported a circle here so that we can have this gear. And what we're going to do, the first thing in making this free body diagram is we're going to write where the points are of contact with our system. So we have these 2 points of contact where gear 2 and gear 4 are essentially contacting with our gear. And we also have a central point where it's attached to the axis. So we'll leave this as the axis. So first things first is we need to figure out in which forces are acting on these points. So if we look back at our diagram, we can start by we can analyze this point first. And we can see that the gear is going counterclockwise. So you can pause the video here and you can try and figure out in which direction is the force from 2 to 3 going to happen, and in which direction would the force of 3 to 2 be happening. So since gear 2 is rotating clockwise, so we can see that gear 2 is rotating clockwise, that means that it's going to be translating a force of going towards the left. So the force onto gear 3 is going to be towards the left at an angle of 20 degrees because that's our 20-degree angle. Okay, so I'm going to copy that over here and I'm going to write it out as the force that we have. So our force is called force 2 onto 3. So it's the force from 2 to 3. So we're doing the free body diagram of 3. So we don't have a force of 3 onto 2. This would be a force of 2 onto 3. And it would be going in the left upward direction because of the fact that we know that the gear 2 is going clockwise and we know that this angle, this force is going to have an angle of 20 degrees essentially. Okay, this is not to scale, it's just to illustrate what's happening, but the angle would be 20 degrees. Okay, then what we can do is we can write the 2 components of that force. So let me just write one component and I'll do them in green so that we can see them. So we have F2 to 3 tangential and F2 to 3 radial. Okay, so we have those two forces acting upon. Now the other thing that we can put is our y and x direction as a standard. So we're going to assume that y is going up and x is going down, and we're going to assume that 2 is in contact with 3 at the bottom of the gear, and 4 is in contact with 3 on the left side or in the x direction from the axis. Okay, so that it's exactly aligned with that level. Okay, so now let's figure out what we have in terms of forces from 4 on to 3. So we can see that 2 hits 3 and essentially creates a force in the upper left direction. And now what we can look at is in which direction would the force of 4 act upon 3. So we see that 3 is rotating in this direction. And since 3 is rotating in this direction, it means that 3 is essentially, and I'm going to draw it up here, 3 is essentially giving a force of 3 onto 4 in the upper left direction, okay? Or in the direction of going upwards and a little bit to the left at 20-degree angle. So that means that the force of 4 onto 3, or the resisting force of 4 onto 3, is actually the opposite. So F43 is actually going in the bottom right direction. Okay, so we're going to draw it on the diagram as well. So let me draw it in black here. So we have a force of 4 onto 3 going in this direction. And once again, we have the two components of that force being F43 tangential and F43 radial. Okay, so we have these two forces acting on our system. Now, those could be the only two forces. However, we also have a third force that could be happening. We don't really know its value, and we don't really know its direction, but we do have a force on the central part on the axis as well. Okay, on the axle as well. And we're going to have to think about that one a little bit, because there isn't always a force on the axle. But if we think about it, the force on the axle is just there to basically balance out the other forces. If we can't balance out the other forces, it means that our gear is essentially going to be going in the downward direction or upward direction. It's going to move out of its central axis. If the gear is not held together, it's going to move in the direction of the two other forces. So if we think of the two other forces and we kind of like map out where they're going, we have one force in this direction and one force in this direction. Okay, so we tend to believe, and this one is a little bit too angled, so I'm going to just redraw it. We have a force in this direction. So if we look at those two forces and we add them together, we can kind of think that our gear, if not held in the middle, would be moving in this direction. So what we're going to do is we're going to come up with a force that is FB3, so F of B3, because B is our axis and it's onto gear 3, would be going towards the top right, somewhere along the lines of top right. And that seems to make sense, because that would basically hold the gear in place and counter this force that would be created by the two F23 and F43 forces. And once again, in this direction, we also have some components of this force. Now, the components of this force are not in the radial and tangential direction. They're just in the y and x direction. So we'll add an x, FB3, and a y direction. Okay, so that basically concludes our free body diagram. So that's all the forces that are happening in our system. And now we have to start solving for these forces. So we know that in order for a gear not to move, we need for all the forces in the y direction as well as the x direction need to be 0. So we can start with calculating for one of them. So let's say that the sum of forces in x is equal to 0. Okay, we know this because if they're not equal to 0, it means that our system would be accelerating towards the left or the right. And we know that the gear is usually fixed. Okay, it's rotating, but it's fixed. So the sum of forces in x is 0, and therefore we can write that if we actually add the components up together of the forces in the x direction, and if we get a direction of these forces wrong, it's completely fine to get them wrong in our free body diagram. As long as we keep our free body diagram based on the directions that we chose or we assumed at the start, if we got our initial guess wrong for the force direction, we're just going to get a negative value at the end. So it actually works out really well, and it works out very easily in terms of, even if you get an assumption wrong, you will get the negative direction of that assumption once you start working out the numbers. So let's look at it. So what are the different components in the x and y direction? So we're going to use the t, the r terms, so the green terms, in order to add all of our systems together. And we would be left with f, so the one that's in the x direction at the axle. So we have fb3x plus f43r. Okay, so we have f43r on the left side here. And then we have a negative f23t. Okay, so these would be the three terms that we have in terms of our information there. Okay, so moving along, we can then try and solve this problem. So what we need to find is we need to find all these different terms. So we need to find fb3x, f43r, and f23t. Now, we know from our equations, we know that Wt is equal to 60,000 times h over pi dn. Okay, we know that term, and we know that that's a given. Okay, so based on this equation, we can then try and identify what Wt would be. So Wt for gear 3 would be equal to the force, or would be equal to F23T. And we can calculate it for F23T based on gear 3, but we can also calculate it based on gear 2. So the other thing we can find is we can find F32T, or the force of F3 onto 2. Now, what we're interested in finding is actually F23T, and if we want to find F23T, we know that that's the force, or the Wt, created by gear 2. So if we look at gear 2 is rotating in this direction, and the Wt for gear 2 would be this, which actually turns out to be F23T. It's the force that's actually happening onto 3. Okay, so we can find F23T through the fact that we have this equation above, and we know h, we know pi, we know d, and we know n as well. Okay, now another important note that we can make here, and this is a new thing theoretically, is that power stays constant throughout your system. So you could calculate Wt anywhere in your system, and the power transmitted would be always 2.5 kilowatts. So it would always be 2.5 kilowatts in the system, whether you calculate Wt at gear 2 or gear 3 or gear 4, it's always going to be the same. So in order to find F23T, the easiest way to do it is to look at gear 2. So we go back to gear 2, and we say we know gear 2 has a certain power associated with it. That means it's going to output a certain force towards the left side. And that force is equal to F23T. And in order to find that force, we have the equation that says F23T, or Wt, is equal to 60,000 h over pi dn. So let's try and solve for it. So if we have Wt, let's write down some of the terms. We have Wt is equal to 60,000. And remember that your units for this are already fixed. So it's 60,000 times 2.5, which is in kilowatts, but we keep it in kilowatts because we know that we have to use it in kilowatts. Then divided by pi times dn. So we don't have d yet, so I'm going to leave it blank or open brackets. So we're going to solve for that in a second. And then N is just 1750 RPM, because that's the RPM that was given in the question for the pinion or gear number 2. Okay, so the last thing we need to find is we need to find the diameter of gear 2. Okay, so in order to find the diameter of gear 2, we need to solve for D2. Now, how are we going to solve for D2? Well, we know that M, or the module, is equal to the diameter divided by the number of teeth. And we're given the module and the number of teeth. So if we rearrange, we can say that D2 is equal to Mn, okay? And it's the module times N2. And so we can say that this is equal to 2.5 millimeters for the module, multiplied by 20 for the number of teeth. So if you had the diametral pitch, you could do the same thing. You could find the diameter through the same equation for the diametral pitch, except the diametral pitch is N over D and not D over N, but it would be the same concept. So based on that, 2.5 times 20 is equal to 50 millimeters. So we're going to use 50 here. And we're going to use millimeters because we know that the units for this is millimeters. So then we can solve for WT, and we can say that WT is equal to 0.546 kilonewtons. Now, direction is very important in this, and so what I suggest you do is whenever you're solving for these problems, you want to tell us the direction of F23T. So you know that F23T is going towards the left, so you can add an arrow on top to make sure that we understand that it's going towards the left. Okay, just so we know 100%. Essentially, the F23T is solved as a positive here because we assumed it to be in the left direction. And since we assumed it to be in the left direction, it's positive in the left, which makes sense. That's why it's positive. Then based on that, what we can do is we can then go ahead and solve for F23R. Okay, we don't really need it as of now, but let's solve it because that's part of the forces that we need. So F23R is going to be equal to F23T. And by essentially trigonometry, we can say that it's equal to that times tan of 20 degrees, which is going to be equal to 0.199 kilonewtons. Okay, and then we can then solve F23 as well as a total force, being F23T over cosine of 20, and that would be equal to 0.581 kilonewtons. So whenever we're asked to find the forces, for me, in terms of a class itself, and whenever you're trying to find forces, as long as you have F23T and F23R, you don't really need to solve for F23. Or if you have F23, you don't really need to solve for the other two because the other two can be solved throughout. Now, in terms of completion, you can solve for everything, but it's usually easier to solve for just those two numbers. Now, how about finding the rest of the forces? So now that we have this gear in the middle, the next thing we need to do is we need to solve for F43. So we need to be able to solve for F43, or we can start with F43T and then work our way to F43R and F43. Okay, so one thing that's very interesting is that one of the rules that we can put in place is that we know that gear 3 is an idler gear. And what an idler gear is essentially a gear that is just there along for the ride, and it's kind of just transmitting force from one side to another of the gear. Okay, and what we typically say is the idler gear has no input torque. There is no torque being input. Essentially, it just transfers power throughout because there's two contact points. one contact point that receives the torque and one contact point that essentially gives out the torque to the next gear. And as such, it means that the sum of the torque, or the sum of the torque around gear 3 is equal to 0. Now, because the sum of the torque is equal to 0, the next thing we could do is we could solve for the torque created by force 2 to 3, and then the torque created by force 4 to 3, and kind of add them together. And then since we know the force from 2 to 3, we can find force from 4 to 3 tangent. But an easier way to do this, and for this type of problem, but you can definitely work a little bit more on this. So one way is you do the sum of torques is equal to 0, and then you do a full torque analysis of the system. So you would do diameter multiplied by all that, and you would work out your torque is equal to 0 and find out that F43T is actually going to be equal to F23T. So let me explain that for a few seconds. So if we go back to our diagram here, we see that, and let's go back to the initial diagram, we see that force is being transmitted through this point. So we have the force being transmitted from 2 to 3, and that force with this gear number 3 is just going to be straight on translated to here. Okay, so that means that essentially 2 is transferring force to 3, and then 3 is transferring the same force to 4, which means that F43T, in terms of quantity, has to be equal to F23T. Okay, it has to be equal to the same. So it's going to be equal to 0.546 kilonewtons. And you can prove this by doing the sum of torques is equal to 0 and actually solving for the sum of torques. But it's not necessary to do so, because you know that essentially the only way that the force is transferred in an idler gear, based on the rule of the idler gear, is through the teeth. So if one force is transmitted from 2 to 3, then it's the same force transmitted from 3 to 4. And F4 to 3 is just the complete opposite. And then we can draw a direction of downwards this way, or we can think of it as F23T is going to be clockwise, and F43T is going to be counterclockwise. Okay, so we could add like a clockwise here and a counterclockwise for F43T. Then we can solve for F43R as well in the same way as before. We get 0.199 kilonewtons, and then F43 is 0.581 kilonewtons, and we can go from there. Now, the last thing we need to solve for is essentially our FB3. And so to solve for our FB3, we can first solve for our FB3 in the x direction, which we can do from, we can recall this first equation that we had come up with, this equation right here at the top, and we can rearrange it knowing that all the forces in x are equal to 0. So we have that FB3 in the x direction would be equal to the other forces in the x direction. So we have F23T minus F43R, and that would be equal to 0.347 kilonewtons. And then we can also do the sum of forces in the y direction, and that's also going to be equal to 0. And FB3 in the y direction, if you actually solved for FB3 in the y direction, you would also get 0.347 kilonewtons. And finally, FB3 could be calculated through the square root of 0.347 squared plus 0.347 squared, just using trigonometry. We would get that this is equal to 0.491 kilonewtons, and that would be in the top right direction as initially predicted. So now we've been able to solve for all the forces in our system, and all the forces are essentially resolved. So if we go back to all the forces on gear 3, we can check that we have all the forces of all the different elements. The one trick here is that gear 3 was an idler, so your F23 force essentially gets translated to a F43 or F34 force going onto gear 4, and hence essentially F23T is equal in magnitude to F43T. If you actually do the sum of torque is equal to 0 around your whole idler, you would actually find the same answer by doing a little bit more math. Okay, and you can do that math in your own time if you want to. Okay, so now we're going to switch to a second problem that we're going to have. So we're going to switch to that second problem, and I'm going to copy it over to our page, and we're going to discuss that problem again, focusing on forces and how they essentially work as a whole. So we've copied over the example, and in this problem, we're going to be looking at something very similar that we've looked at just to practice and kind of understand what's happening with a slightly more complex system. So it says here that the gears shown in the figure have a module of 12 millimeters and a pressure angle of 20 degrees. The pinion rotates at 1800 RPM clockwise and transmits 150 kilowatts through the idler pair to gear 5 on shaft C. So we can see that here in the question, we already get this hint that we learned that the 150 kilowatts gets transmitted throughout. So the power is throughout 150 kilowatts, and it gets transmitted to gear 5. What forces do gear 3 and 4 transmit to the idler shaft? So we're told to find the forces that gear 3 and 4 are transmitting to the idler shaft. Now, if we were to draw this system on the side, we would have gear 2 attached to gear 3, okay, which would also be attached to gear 4, and then gear 5 would be essentially attached to gear 4. So we'd have 2, 3, 4, 5, which we've seen in the past already, and I'll just add some shafts here, which we've seen in the past already, but essentially gives us an idea of how it would look like from the side or from the top if you were looking at this system. Okay, so looking at this system, we can now start analyzing the system. So it says, let's look at the information that it tells us first. So we know there's 150 kilowatts through the idler pair to gear 5. We know that the pinion rotates clockwise. So let's start working on our directions of rotation. So we know that the pinion is going clockwise. It has 18 teeth. So that means that gear 3 is rotating counterclockwise. Now, be careful with this, but gear 4 is also rotating counterclockwise because it's attached through a shaft, and then gear 4 is attached to gear 5, and therefore we have gear 5 is going to be clockwise. Okay, so we start with clockwise and we end with clockwise in this case. Okay, so then it tells us to look for forces that are happening, that are transmitting through gear 3 and 4. So where I like to start these problems, and the last problem we kind of did the same thing, but we took an extra step, is we know we have to find the forces on gear 3 and 4. So we're going to draw a free body diagram of gear 3 and 4, but before we do that, so I'll just write free body diagram of gear 3 and 4. And that's going to allow us to basically solve our problem once we have all the forces on gears 3 and gear 4, because we're looking for all the forces that are acting upon the axle or that are acting towards the axle. So we're going to do this, but we're going to wait a little bit later on. So I'll write, but first, the first thing we can do, and we know that we're going to do this in the majority of the cases, not always, but it is very helpful, is to first figure out what our WT is, okay? We can find WT from 2 to 3 because we're given all the information on the pinion, and since we're given all the information on the pinion, we can solve our WT. And then once we solve our WT, it makes it a lot easier to solve our problem in general. So we can do a quick free body diagram of gear 2, just so we have it. So this would be gear 2, okay? We have a certain torque from A to 2 that's happening. This torque from A to 2 is clockwise because we know that gear 2 is rotating clockwise. And we know there's one contact point on gear 2, and we know that that contact point would have a force of F32 onto the gear, and then that means that there's an F32R and an F32T as a reaction from gear 3 to gear 2. Now we also know that if we look at the bigger picture, we also know that WT, okay, if we've just looked at the bigger picture, we also know that WT would be the force, tangential force, happening in either the clockwise direction or the counterclockwise direction. It doesn't really matter. The direction doesn't really matter. The important thing is the value that we get from WT, because we know that WT would be equal to, for example, F23T, which would be the force transmitted from 2 to 3. And we know that the magnitude of F23T is equal to the magnitude of F32T as well. Okay, so the magnitudes are the same, it's just the direction just changed. So let's first solve WT. So compared to the first example where we solved where we solved our free body diagram first, this time we're finding WT first because we know we're going to have to use it probably. Okay, so based on that, we're then going to say, okay, let's find WT. So first things first, we know that D2 is equal to M times N2, which is equal to 12 times 18. So we have a value of 216 millimeters, okay, given to us. And then based on that, we know that WT is equal to, once again, we're using SI units, but there is a US units equation as well, times 150 kilowatts divided by pi times 216 multiplied by 1,800, which is the RPM at which gear 2 is rotating at. And we get that this is equal to 7.368 kilonewtons. So based on that, we can then write that we know that WT is equal to F32T, which is equal to F23T, and has a magnitude of 7.368 kilonewtons. Okay, so that's going to help us in solving the problem and solving what's happening in terms of our gears themselves. Now, the other thing we can do really quick, just to complete the diagram and complete the force diagram here, we can also say that F32R, and this is really like the free body diagram of 2, F23R would be 2.682 based on trigonometry. So I'm not going to go over trigonometry, but hopefully you remember how to do basic trigonometry. The next thing we can do, and we might not need this for now, we could need it if we were asked for the torque, we could also find torque A2. And we can say that torque A2 is equal to WT times D over 2, or diameter over 2. So we would get that this would be equal to 795.7 Newton meters. And you just need to be a little bit careful with your units here, okay? You just need to be careful with units because you have kilonewtons as a force and millimeters, so it actually works out with the units. You just have to be a little bit careful. Okay, so the next thing we're going to do is we're going to recall this free body diagram. So I'm going to draw an arrow here so that we have it in our notes. Okay, I'm going to continually write the arrow down, and we're going to bring our free body diagram of gears 3 and 4. So I'm going to draw, and this is where it gets a little bit more complicated because we have 2 gears on top of each other, and we need to think of the free body diagram with the central axis B. Okay, and there's 2 contact points mainly on this idler gear. So once again, it's an idler gear, so there's no torque, or an idler pair, there's no torque. So we'll take that into account. And we have 1 contact point here and 1 contact point here. And we can write the forces that we have. So we know that the rotation of these 2 gears is counterclockwise. So we know it's rotating counterclockwise. And we have the 2 main forces attached to our system. So the 2 main forces that are happening is we have a force coming in from the bottom left, which is F23, okay? F23 being our force from from pinion 2 onto 3, okay, we actually already know the value of F23, or at least we know the value of F23T. And then here we would have a reactionary force coming from F54, very similar to the previous example. And then we have each component of that force, which I'm not going to draw here because you already know the components and how they work, but you can draw them for your own sake. Now, the first thing we can do is, since we're asked to find all the forces on shaft B based on the idler pair, well, we already know what force F23 is, so let's write it out. And let's make a box, and let's say this is our final answer for the forces that are F23 based on our system. So we have F23T is equal to 7.368 kilonewtons. And then we have F23R is equal to 2.682 kilonewtons. And we know that all these forces are in the relative direction that is to the right and up, okay, just so that we know what direction we're talking about. And obviously you can find the actual value of F23 if you wanted to, but it's not necessary to find it. It's actually easier to solve our problems using tangential and radial components, so we don't actually have to find these values. Now, in a test, this would be perfectly fine to leave your answer as is. For the 2-3 part, I don't need more information. Obviously, if you wanted to, you could sum all the forces in X and sum all the forces in Y at the very end, but we're not going to have to do this time. So the other thing is, so I'm just going to write it down so everybody has it within the notes. Because it's an idler pair, we know there is no torque. And this time, we're actually going to use the sum of torques is equal to 0 equation, because it's a little bit more complicated to find what F54 is. So in the previous problem that we had, it was very easy to find F43, or the reactionary force of F4 onto F3, because we had both forces on the same gear. In this case, the two forces are on the different gears. So in order to satisfy that the torque is equal to 0 due to an idler pair, the force from 5 to 4 is going to have to be much higher because it has a smaller moment arm. Okay, you can clearly see the distance between B and basically the radius of 4. And let me annotate the gear numbers just so we have them. So 3 and 4. The radius of 4 is much smaller than the radius of 3. And therefore, the force 5-4 is going to have to be much higher. So what we can do is we can actually use the torque equation to see how it would actually work. So we know, because it's an idler pair, we have a sum of torque is equal to 0. And now we can just write the torque out. So the radial component of our force is useless for torque because it's in the same direction as the center. So there is no torque associated with the radial component. So essentially what we're looking at is tangential component of force multiplied by the distance to find the torque. So we have that the torque, assuming that clockwise is positive, is going to be equal to F54 tangential times D4 over 2, okay, or radius of 4, minus, in the counterclockwise direction, F23T times D3 over 2. And we can find, we already have F23T, so we're good with that. And then D3 and D4 we can find through the module. So we can solve for D3 and D4, and I'll just write them down so you have them, but you can solve that in your own time if you want to. Is 384 millimeters for D3 and 216 millimeters for D4, and that would solve that essentially by rearranging the equation above. We would have that F54T is equal to 13.1 kilonewtons. And then from there, we can solve for F54R, which is equal to 4.768 kilonewtons. And these are, and so we can add the direction of these forces is this way. And essentially what we've said is that these forces are, so summed up, if you had F54T, F54R, and then F23T and F23R, these forces would be the forces acting upon shaft B. So one extra step that you could take is you could sum all the forces in the X and Y direction and find the forces of gear 3 and gear 4 onto the shaft, but they're already kind of found. They're just in tangential and radial form. So if you wanted to, you could go one step further and write them in the Y and X direction and kind of sum them up if you wanted to. If not, this would be enough information for us to solve the problem of saying that what forces do gears 3 and 4 transmit to the idler shaft. Those are the forces that would be transmitted to the idler shaft, the F23 and F54. Okay, so in the next lecture, in the next video, in the next lecture, what we're going to do is we're going to do an extra example problem. And this extra example problem will ask you to find the force and the torque as well on the final gear. So we're actually going to use a little bit more things about, we're going to look at the final gear as well as the idler gear as well. So we'll see you in that video.